Good morning, everybody. From this part of the world, which is, I'm from Hyderabad, India. I'm sorry that because of different time zones, some people might be having difficulty in it could be very late for them, or it could be very early for them. But that's how things are happening nowadays. So I think let me just give a small background to this session. So first of all, let me welcome all of you to this session on deformation of the Antarctic plate, influence of tectonic, volcanic, hydrological, and climate change processes. My name is Vineet Gahalaut, and I'm your convener for this session. I'm based in Hyderabad, India. We work closely with NCPOR, which is the host institute organizing this conference, which is based in Goa. We have two bases in Antarctica, one at Mathri, which is an old one, and then there's a new one which has come up, which is known as Bharati. I'm basically a tectonic geodesist or seismologist in broad sense, and I'm trying to understand the deformation on short and long-term geological and tectonic processes. We designed this session to deal with deformation of the Antarctic plate due to geological process starting from formation and breakup, long-term deformation due to geological and volcanic processes. It also includes understanding plate motion, volcanic deformation, and glacial isostatic anomaly, GIA, in short, what we call it. It also includes understanding short-term deformation, which could be through earthquake cycle, having phases of interseismic, coseismic, and post-seismic deformation. At least I'm very optimistic that we will be through this deformation, through looking at this short-term deformation. If we have longer time series, we may be able to understand the role of climate change on the deformation. So that's something which I'm hoping for. One can also do some glacial movement studies through deformation measurements in Antarctica. Seasonal deformation is becoming more challenging, which is, again, it could be annual, and it's mostly because of hydrological load, and that's the problem is that it contaminates the long-term or the circular motion of the plate or the motion through the earthquake cycle. So it's important to understand the seasonal deformation. So these were the themes which we thought to include in this session, and fortunately we have abstracts on many of these issues. In total, we had 16 abstracts, and out of which 12 are oral presentations and 4 are posters. So I encourage all of you to look at these posters. These posters are available for viewing at, if you go to ePoster, then go to geoscience section, and then go to deformation of the Antarctica. That's our session. You will be able to see these 4 posters. I could see at least 3 of them. I'm not sure about 4th. Till evening, my evening, there were only 3 posters which were there. 4th one is, I'm still not sure whether it is submitted or not. But nevertheless, you can see the abstract. So I request all of you to visit these posters and spend some time on these posters. You can raise your queries on these posters. These posters, as I said, these are 4 posters which I saw. So there's the first poster, which is beautiful poster, which I liked very much, was Guy Paxman. It deals with total isostatic response of the complete unloading of Greenland and Antarctic ice sheets. That's a beautiful poster. So it basically deals with a GIA model. So they use a flexural model, use elastic or viscoelastic earth model. And the whole idea here is to look at the deformation over a long period, not exactly long period, but over 1,000-year cycle, right? Probably since last Glacial Maximum. So it's a beautiful poster, and you should certainly see this. There's a second poster, which is by Mariano Augusto. That's on chemical composition of acidic gases from fumarolic emissions at Deception Island, volcano, Antarctic. The content of the posters are clear from the title itself. So they deal with a very active volcano, which is at Deception Island in Antarctica. So they try to understand the chemical composition of these fumarolic gases which are coming out from this volcano. And the idea is that this analysis will help them in understanding the process, controlling the activity of magmatic hydrothermal system. The third poster is by Paula Sainafara. I'm sorry if I pronounce the name wrongly. Please excuse me for my bad language. So this is on deciphering the sub-ice basement architecture of the Ranic Aviated Fault Zone, insight from outcrop scale fracture analysis. So basically, this is to do with mostly structural analysis of northern termination, structural analysis of the region. So they analyze the structural pattern of the northern termination of the trans-Antarctic mountains in North Victoria Land. The fourth poster is by Pedro Henrique Almeida. So that deals with use of LIDAR data to identify mass movement processes on the Peninsula, King George Island, Antarctica. LIDAR is becoming very popular nowadays, and this is basically to show the ability of LIDAR measurement, which gives you higher resolution aerial images to identify geomorphic process in the large areas. So it made it, these data made it possible to cover inaccessible areas and identify small changes in the terrain. So these are the four posters which are there, which you can view all of them. So let me come back to now the oral presentation. So for each presentation, we have given 15 minutes time, which also includes time for discussion of about 3 to 5 minutes. Since we have enough time, so we can slightly relax this time. We can at the most we can go up to 5 to 7 minutes of discussion. Please mind that this session is being recorded. So you and your PPT, everything will be available on YouTube after this conference. In case you have questions, then if you want to ask, then it is good to ask it through chat box in the Zoom meeting. So that's the introduction kind of thing I wanted to give, and I think we can start now. And I guess the first presentation here is by Grace Neal, which is on post-seismic deformation in the northern Antarctic Peninsula following the 2003 and 2013 Scotia sea earthquakes. I guess that Grace is not attending this meeting, if I'm not wrong. Let me try to see if she's there. I don't see her here. So probably she has uploaded her presentation on the dashboard, and I request tech team to start this so that we can see it. Oh, thanks, Matt. That's so nice of you. Oh, I see that we don't have any video. Matt.
Yeah, Vineet, I was expecting, certainly Grace said she was going to upload a video, so I don't have the presentation, so I can't deliver it. So that's really unfortunate if it's not there.
Tech team, can you confirm? Because I remember that she sort of communicated that she has uploaded the video. Tech team, if
yes,
bandwidth
I'm just
is,
having a look. Just give me a minute.
sure. If bandwidth is not an issue, then can we see? Can you put your video on so that, you know? Otherwise, it looks like we are talking to some Alexa or Siri.
Just give me a minute, sir. I'm just figuring out something.
So maybe Hector, Eric, Junio, you can put on your video. That's so nice.
Sir, if you could move to the next presentation, I will keep it ready.
That's a very good idea. Or maybe if Matt can find, if the time is not very inconvenient, can find this PPT, we can take it later on.
Yeah, Vineet. So I don't have a copy of the PPP, the PowerPoint myself. So, but I mean, I can certainly happy to go on with my presentation if you wish to.
Sure. So the next in case we find Gray's presentation somewhere, we'll come back to it at the end. But then the next presentation is by Matt King, which is on GPS rates of vertical bedrock motion. Suggests late Holocene. I'm sorry, there's some. Suggests late Holocene ice sheet re-advance in a critical sector of East Antarctica. Matt, please go ahead.
Thanks, Vineet. And I think you can see my slides. Okay. Yeah, good. So this is work that's been done in combination with Christopher Watson here at the University of Tasmania and Dwayne White at the University of Canberra. All the work that I'm going to show today has been published a few months ago in GRL, and I'll show you that at the end. The sort of the continental view of models of glacial isostatic adjustment show that there's quite a lot of disagreement, perhaps not as much disagreement as there has been in the past. I think there's sort of a slow convergence. The forward models that are on, so this is a figure from Whitehouse and others, 2019, showing a group of predictions of present day vertical land motion due to GIA. Most of the models are forward models of GIA, and the three in the bottom, on the bottom row on the right, are inverse solutions. The forward models come from ice histories. It's important to note the ice histories are all, as far as I'm aware, monotonic in terms of the ice retreat. So the ice either is stable or retreats. It doesn't re-advance at all in any of these models. And there's obviously relatively simple rheological models in many of the cases, mainly Maxwell rheologies, but that's not the only rheology that's adopted. There's some power law rheologies in this mix. The inverse solutions are based on a range of geodetic data sets, and we won't go into the detail of them. That continental level view gives you the impression that the models are in relatively good agreement in East Antarctica, but actually they sort of hide some disagreement. And so this is a zoom in on a sector of East Antarctica from effectively just east of the Amory Ice Shelf through to east of the Totten Glacier. And you can see here by looking at the different color scale to what was on the previous slide, substantial variation between these different models. I6G, prominent model in the predicting fairly strong uplift around the just interior of the coastline of this region of East Antarctica, up to 3 or 4 millimeters a year. The Ivans and James model, by contrast, predicting actually almost no uplift, just slight uplift for most of this region. The Whitehouse and others model showing strong uplift in the Totten Glacier region, but very little elsewhere. And then a range of geodetically informed models, which all show, well, I think strikingly different patterns. Most of them showing uplift around that continental margin. But this solution by Zhang and others showing some significant subsidence in this area as well. And the most striking of all was perhaps the Gunter and others model, which was showing very strong uplift in the interior of the ice sheet, and actually led to some of the thinking behind the study that that we proposed to collect some more GPS data. So this is now showing in the top left-hand corner some of the new sites that we've deployed, new GPS sites. The sites at Davis and Casey are, of course, the long-running IGS sites. The site here at Bunga Hills was previously established by Geoscience Australia, but we've extended it. And then 3 other sites where we're, in addition, we're going to look at today. This one in the southern region of the Denman Glacier system, well upstream of the Denman Glacier, one just to the west of Casey, and one to the east of the Totten Glacier here, and in a very rare piece of bedrock outcrop. And I think the next piece of outcrop to the east is probably another 1,000 kilometres. There's 3 other sites here shown in red that we have established, but we don't have sufficient data yet to be able to report on the time series. This is just a quick visual of the typical GPS site, very similar to the GPS sites in West Antarctica, a sort of PoleNet style monument with a choke ring antenna and radome. In West Antarctica, there's been significant issues with icing inside these radomes, mainly due to, it seems like, snow penetrating through the drainage holes in the base of the choke rings. And so we got onto that relatively quickly, and these were plugged, and we haven't seen any substantial icing problems. Antenna cable running down to a power system down here. This is just north of the Antarctic Circle, so there's actually relatively good sunlight year round in this region, and we get with one solar panel and a battery or 2, we get near year-round operation at these sites. We also have co-located seismometers from a project that Professor Anya Redding is leading in conjunction with this project. So we do some GPS data analysis. We have a fairly conventional analysis approach. We're looking here at data from about 2002 to 2021. We're using the Gypsy 6.4 software in PPP mode. We use the JPL clocks and orbits. The solutions are in the IGS 14 frame. Because we know pretty well the atmospheric loading, we compute and remove the atmospheric loading displacements. That just removes the source of noise. It doesn't really bias the velocities, it just increases the uncertainties. And one of the things that stands out straight away here is this sort of apparent long-term subsidence at Mawson and Davis, and certainly strong uplift that varies over time at Casey. And these sorts of things have been reported on in several previous publications. You also can see the Bunga Hills site with the earlier part of the record, and then the extension that we've got, noting that there's no hardware changes here. So this is a continuous record without the antenna being removed or the receiver being changed. And then the very much shorter time series associated with these new sites. And one of the things you can see is there's some non-linearity here. You can see that at Casey, and you probably expect that from Totten Glacier. Certainly see it at Davis, that's not so well understood. And a bit at Mawson, but Bunga Hills, this doesn't look like necessarily a straight line. And so that's one of the things we're going to be thinking about as we go through this talk. One of the things we're interested in is, well, what's the effect of time varying surface mass balance? So this is the surface mass balance in Antarctica is effectively the precipitation. There's some other processes that are going on, but you can think of it just as precipitation. Surface mass balance models are not like hydrological models in that they don't include discharge from the ice sheet. So we're just thinking about surface mass balance here, and to do that, we assume that the ice sheet is in balance, and then we come back to that later on. We're testing two different surface mass balance models with slightly different spatial resolutions and different forcings and different parameterizations. And we look at three different elastic Earth models, one from PREM, another one AK135, and then a regional version of the Lloyd elastic model. So we take a 1D section through that 3D model and use as appropriate for this region and use that. And so what you can see here on the right is some computed displacements for the Bunga Hill site from the 1979 through to 2020. You can see the total displacement, varies. There's some seasonal signal in here, but not every year. There's some interannual variability in here, and there's some longer term, very long term periodic displacement, and that sort of marries up with some work that Chris Watson and I published in GRL a couple of years ago, where we look back even over 200 years, and you see the greatest power at the lowest frequencies at the longest periods. And that's what we see here, that the greatest variability in displacement is actually over the longest periods. And if you drew a line through this later part of the record from 2010 onwards, that's about heading towards 10 millimeters over 10 years, and at a higher rate even in the last 5 years of the record. So this is a fairly substantial potential bias in this site at Bunga Hills. What's interesting though is that it doesn't really matter compared to the size of that signal, at least, which elastic Earth model you use. We adopted the AK135 because it was marginally closer to this 3D elastic Earth model of Lloyd. And so while most people would adopt PREM often as a conventional model, we've adopted the AK135 for this. But we don't revisit the elastic Earth model afterwards. One of the things that is important though is the choice of surface mass balance model. And so here we've got two different variants of each model for three different sites. So if you look at the blue lines, we've got in the thicker line, we've got the RACMO surface mass balance model. The thinner blue line is the one that I've just shown you below. And you can see that there's substantial variation over different periods of time, but the two models reach quite a lot of convergence around 2010 and certainly track each other very closely thereafter. Davis, we see much less variability total and lower amounts of difference between the two models. And at Casey, we see substantial signal, but pretty good agreement actually between the models through most of the periods, although there's some interesting features in there. So if you're working with surface mass balance data, it's important to think about perhaps more than one model. So we include that, so we compute that, and we're going to use the rest of this study the MAR model with the AK135 elastic model, but recognizing that before 2010, there might be some differences. And we subtract that from the GPS time series. What's interesting when you turn those different time series, and here I'm showing not just the colored lines, which is shown here, but the gray lines are a subset of 230 sites distributed across Antarctica from the Regain network that Eric's going to talk about later on. It just gives you a sense of the variability at other sites all around Antarctica. If we compute the power spectra for these, colors in terms of blue, green, and dark blue are the same as for the time series. You see there's a power law-like behavior to these spectra in a log-log system. And that is approximated by a flicker, so a random walk type scenario, so well above flicker noise. So it seems like this surface mass balance loading data is contributing random walk-like noise to GPS time series. And just to compare, and the median of all of those 230 sites or so is this line in pink. That's also showing random walk-like behavior. If you compare it to the atmospheric loading median across all those sites, well, you see effectively white noise coming from the atmospheric loading. And so that's not going to affect the velocities over any particular time period, but this surface mass balance loading is concerning when you're trying to get to surface velocities such as for GAA. And then if we subset these simulated time series into different periods of time, then you can see that even over 11 years of data span, it's not unusual to have surface mass balance loading that equates to plus or minus a millimeter a year or thereabouts, even higher than that in some of the sites sometimes, due to surface mass balance loading. So these are concerning amounts of signal from things that we tend to think are just sort of often have thought about as effectively as noise in the GPS time series. They actually can be substantial systematic biases. The other thing that we notice is that there's common mode error in the GPS time series. I'm plotting here the Bunga Hills time series that I showed you before. It's the time series here is in blue. For the moment, you can ignore the red line, but you can see that it's not linear. There's some ups and downs, and they're considerable. You may not be confident in putting a straight line through that time series. What's interesting is if you subtract it from the Davis time series, we see that something that's substantially more linear, but also we see something that's pretty flat, indicating that the Bunga Hills site is probably has a similar long-term velocity to Davis, and recalling that Davis is going down over 20 years or so. So we computed, we thought that that was evidence of common mode error, probably coming from the satellite orbits and clocks that particularly PPP solutions are sensitive to. So we computed a complete ensemble empirical mode decomposition with adaptive noise. It's like a empirical mode decomposition, but with improved characteristics. We're a bit challenged here in terms of often with common mode error, you would use a network of stations, you do some averaging or some sort of EOF analysis. We have very few sites nearby that are long running and continuous that we can do that with. Casey is affected by the mass variability of the Totten Glacier. And then the next nearest continuous site is Mawson, another 750 kilometers or so to the west of Davis. So what we do is we just do the SEAMDAN analysis on Davis only, recognizing the potential weaknesses of that approach. We adopt the low frequency of modes from that analysis and the non-linear part of the lowest frequency mode, and then we sum them up. And what we sum up is the red line here plotted over the Bunga Hills time series. So you can see that that seems to pick up a lot of the variability. And of course, that's what we expect because that's what we saw when we differenced the two time series. Now, when we subtract off that common mode error, this is the time series we get. It's not perfectly linear still. And we've plotted over the top of that a range of elastic deformations from the surface mass balance models through here, and also a separate one from based on satellite altimetry. And I won't talk further about that for now. So if we then subtract the surface mass balance with MAR off, then again, we're now getting increasingly clear subsidence at this site, and I think increasingly clear linearity. And you can see what happens when you use an alternative altimetry model as well. So we then take that common mode error as being coming from the orbits and clocks and propagating systematically and identically across the whole network that we're processing, and we subtract that as a common mode error. Now, the results suggest widespread subsidence in this region. This is a complicated plot, so I'm going to step you through it carefully, I hope. So we start off with the red dots at the different sites. These are going from west to east. Here you can see the distance from Davis, and this is in uplift rate. And we're going to look first of all at the red dots, which are the GPS minus atmospheric pressure loading displacements and the velocities of those. So the red dots suggesting Davis going down at something towards 2 millimeters a year, Bunga Hills going down at something like 0.5 millimeter a year, Casey going up at 2.5 millimeters a year, and some of these other ones going up at 3.5 millimeters a year. So then we subtract off the common mode error. That's we're going from red to purple now. You can see it has a very small effect at Davis. At these very short running sites that are 3 or 4 years long, we're seeing something of the order of 2 millimeters a year impact because it just happens to fall in a period where there seems to be very large common mode error. But much smaller effects at Casey and at Bunga Hills, as you'd expect, because the common mode error is sort of average over longer periods of time. Then we remove the surface mass balance loading effects. That takes us from the purple to the green. Very little effect at Davis, again at Bunga Hills, and at, a little bit of an effect at Casey. Certainly a lesser effect at those sites than you get at the shorter running sites. And you'll remember that actually at some of these sites that were only running for 4 years, it was in that peak period of time where the surface mass balance loading in the Bunga Hills area was really large. So this site here, CAD 4, is really quite near to Bunga Hills, and you see a very large change from say 1.5 millimeters a year uplift to heading towards 1 millimeter a year of subsidence. And again, other effects when we remove that. And so that the green dots are our preferred solution. We think there's good evidence for both common mode error and certainly for the surface mass balance loading. And that leaves us with subsidence at Davis, subsidence at CAD 4 at Bunga Hills, and then starting to increase as we get towards Casey, and then uplift at Casey and uplift further to the east at this site at Chick Island. If we use different altimetry-based loading models, which includes the effects of mass loss in Denman Glacier and the Totten Glacier, we see similar but different signals. But we see widespread subsidence, certainly from Davis through to the Bunga Hills in this region. If we put that on a plot, on a map, we see that none of the models does a great job in terms of agreeing with the GPS. You need to think about the uncertainties here. They're about 0.5 to 2 millimeters a year, depending on the site duration. Probably the best agreements with the W12 model in terms of the forward models, but the Z19 inverse solution does well, and that's interesting. Now recall that Mawson, which probably is about 750 kilometers further west, is also subsiding in the long-term GPS record. So we've got subsidence at Mawson, subsidence at Davis, subsidence at the Bunga Hills region, and then uplift in the Totten Glacier. We think that's due to ice sheet readvance during the late Holocene, at least in parts of this region. There's pretty limited geological evidence in this area, but what there is certainly doesn't disagree with that idea. And readvance is not included in the forward models. I have very little knowledge, understanding of why the different geodetically informed models are so different, but also generally disagree with the GPS. We certainly see uplift in the Totten region, and large scale retreat from there is pretty well understood. And all of that information and more is provided in this paper that's in GRL. And with that, I'll thank you for your time.
Thanks a lot, Matt. Thanks a lot. In case you have a question, you can put it in the chat box. I have just one question, which Matt, if you want, you can see it on the chat box. It's a question of general interest. I mean, we do see some earthquakes in Greenland because of glacial rebound, that they have been ascribed to be triggered by a glacial rebound. Do we have any evidence of earthquake triggering because of glacial rebound in Antarctica?
So that's a good question, Vineet. So there was a magnitude 8.2 in 1998 in the Balleny Islands, just north of Victoria Land in East Antarctica. There is some papers, well, at least one paper by Eric Ivans as a co-author on that, where there's a suggestion that that is GIA induced stress changes in that region. But there's been very limited work. And that's the only piece that I know of in at least the modern era.
Thanks, Matt. Thanks a lot. I think we have sort of slightly exceeded the time, but that's perfectly all right. Beautiful presentation. Nice work, Matt. Honestly, I'm very much interested in such things, so that's why I didn't interrupt you. Thanks a lot. Thanks a lot, Matt. And what we're going to do is we are going to take the presentation by Grace now. We have found the video. So Matt, please stay with us so that in case there are questions, you can respond to them. So tech team, can you play the presentation by
Hello
Grace.
everyone.
Yeah.
Today I'm going to talk about post-seismic deformation in the northern Antarctic Peninsula following 2 earthquakes that happened in the Scotia Sea. This research has been funded by the Australian Research Council through a grant at the University of Tasmania in Australia. Post-seismic deformation in Antarctica is not well studied. However, King and Santamaria Gomez showed in their 2016 paper that the continent is undergoing post-seismic deformation following a large earthquake that happened in 1998. This earthquake occurred around 600 kilometres from the coast of Antarctica and caused widespread horizontal and vertical deformation across the continent in the years following this event. This is important because this post-seismic deformation signal affects geodetic measurements that are used to constrain geophysical models such as glacial isostatic adjustment. The work that I've been doing is to investigate whether the Antarctic Peninsula is affected by a 2003 and 2013 earthquake that happened in the Scotia Sea, and if there is deformation there, how much, and whether we can constrain Earth properties by studying these earthquakes. These 2 earthquakes occurred at the plate boundary between the Scotia Plate and the Antarctic Plate, around 700 kilometres from the tip of the Antarctic Peninsula. They were quite large events, 7.6 and 7.7, and both strike slip events. We've been able to see post-seismic deformation in a GPS record from the very tip of the Northern Peninsula at O'Higgins, and this record clearly indicates post-seismic displacement at the time of this 2013 event and subsequent post-seismic deformation. And we're able to use GPS records before and after this 2013 earthquake to try and investigate the kind of post-seismic deformation we might expect and aim to place some bounds on the Earth properties. So we do this by running a model for post-seismic deformation. And the first thing that we need for our model is the fault geometry and post-seismic slip parameters. We take these from the study of Yi et al. 2014, and we approximate the values that they solved for in that study. We have a simple rectangular fault plane that's divided into 3 sections, each with a different slip and rate. In the figure here, you can see the values that are input on the finite element nodes of the model. So this information is input into the finite element model that predicts post-seismic displacement and subsequent post-seismic deformation. This is a finite element model, and it's spherical and global. It's been built in the commercial software Abacus. The earthquake is simulated in this model by prescribing post-seismic slip on a fault plane that is cut within the mesh. Subsequent viscoelastic relaxation follows the post-seismic slip according to the stress changes within the model. This has been validated against the Okada co-seismic solution and the Visco 1D software from Palette. So once we've run this model, we can compare the model predictions to GPS time series. So we can detrend the time series to obtain our post-seismic deformation, and we can compare the model to the observations. We first also make an additional correction to the GPS observations to account for GIA. So in the northern Antarctic Peninsula, there is quite a lot of ice mass loss related to the collapse of ice shelves, particularly the collapse of Larsen B in 2002. And following these ice shelf collapse events, there have been a speed up of the glaciers and mass loss on the northern peninsula, and this is causing a sort of short-term GIA signal, which is occurring on the same time scale as post-seismic deformation. So we make an additional correction to the GPS to try and remove this signal. We can then refine our Earth properties and test a full suite of different Earth structures to try and place bounds on the likely Earth structure in this region. So first we test a simple 1D Earth model. with a Maxwell rheology. So we have a 4-layer model that consists of an elastic lithosphere, a low viscosity asthenosphere, and an upper mantle with a low mantle below. We varied the thicknesses of these layers and the viscosities. We also test a simple 1D Berger's rheology, where we have a transient viscosity that is 1 order of magnitude less than the steady state viscosity. We also test 2 different kinds of 3D Earth modelling. The first one mimics the presence of a former subducted slab under the Northern Peninsula. As you can see in the figure here, this subducted slab dips down towards the east from the South Shetland Trench. In cross-section, we can see that the high viscosity slab dips down and we have a low viscosity wedge above it. And again, we vary the thicknesses of the layers and the viscosities as well. The second 3D Earth model that we test is derived from seismic data. So we use the M20 model from Lloyd et al. 2020. And where we see lateral variations in seismic velocity, these translate to lateral variations in viscosity. So where we see low seismic velocity in red, this translates to low viscosity. This is combined with a power law rheology, which is a laboratory-derived flow law. So once we've got our suite of different Earth models and we've predicted the post-seismic deformation following that 2013 earthquake, we can plot the results. So this is the east displacement for GPS locations running from north to south. And we can see that the signal diminishes as we move south away from that earthquake, where we have actually quite a significant amount of displacement at O'Higgins right in the north of the peninsula from some of these low viscosity models. We see a similar trend with the north displacement, although slightly less displacement in the north direction than the east. And for the vertical, we actually see some subsidence, although because this is a strike slip earthquake, we don't see very much displacement in the vertical direction. So we're able to compute a WRMS error, which is going to help us identify those best fitting Earth models. We do this for the east and the north directions only, and that's because we have minimal displacement in the vertical, and the vertical GPS is also it's more sensitive to that GIA correction that we've made. We use a subset of the GPS time series, those with a reliable estimate of post-seismic deformation and those with minimal data gaps. So here we have a viscosity plot with depth. So this is for the top 400 kilometres of the Earth, and we can see in grey all the different models that we've tested, and in red the best fitting viscosity profiles. And the same with this figure for Berger's, where we can see actually our best fitting model is quite tightly constrained. We seem to want quite a thin elastic lithosphere and an asthenosphere of between 120 and 190 kilometres with a viscosity of 3 to 4 times 10 to the 18. And we do get similar results for these Maxwell and Berger's models. So if we have a look at one specific time series now, this is for O'Higgins in the east direction, and we can compare all our best fitting models on this figure. So here's our Maxwell best fitting model, the Berger's, which we get a slightly lower minimum WRMS error. We have that first 3D model there as well, which gives us a similar result, and a 3D power law model, which is derived from the seismic data, gives us a slightly worse fit. So it seems that our model prefers a Berger's rheology. We want to just have a look at this in a bit more detail, because Berger's rheology has that transient and steady state viscosity, so we want to investigate that transient signal a little bit more. And we do this by recomputing this model, which has been run at 1 year time steps, at a higher temporal resolution to see if there's any signal that we're missing. So we rerun this model with 2.5-week time steps in the first 2 years, and we can see that there is we get a more significant transient response from that model that's being run at a higher temporal resolution. But what's interesting is that we actually don't see this signal mimicked in the GPS. So that suggests that maybe this transient signal is beyond the detection level of GPS, or it might be being masked by other signals, such as seasonal signals, which might be occurring on the same timescales. So next we can have a look at the 2003 earthquake. We don't have enough GPS observations before and after this earthquake to go through the same process of constraining Earth properties again. So this time we just use the Best-Burgers model that has been constrained from the 2013 earthquake and run a forward model. The slip properties again we've approximated from EFL 2014, and again we've got a fault plane with 3 sections of different slip and rake. So what we see from that 2003 earthquake is small horizontal displacements. So the blue arrows here showing less than 0.5 millimetre per year horizontal displacement in the sort of 6 or 7 years following that earthquake. If we compare that to the 2013 earthquake, the green arrows there, we can see a lot more displacement from that second event. It's interesting also to note that O'Higgins is moving around 2.3 millimetres per year southeast, which is a bit of an anomaly. This has been reported by Argus et al. 2011 and 2014, and they showed that O'Higgins is moving in an opposite direction than expected from ice loss, and the cause of this is unknown. So we suggest that potentially there's a contribution from this 2003 earthquake. The data they used actually predates that 2013 earthquake, so it's not due to that, but I think there is a small contribution from this 2003 earthquake and potentially from other earthquakes that happened before this. So if we combine the results from the 2003 and 2013 earthquakes, we get quite a significant amount of horizontal displacement. And if we flip forward through time, in 5-year increments, we can see that this signal persists around 50 years after this event. And the magnitude of the displacement diminishes, but it's still persisting after 50 years. And interestingly, the direction of the velocities is changing through time. So to sum up, the Antarctic Peninsula is undergoing post-seismic deformation due to these 2 earthquakes that happened in the Scotia Sea. And we see up to 1.5 millimetres in the east direction. Comparing the model output with GPS time series, we are able to constrain an Earth model with a Burgers rheology and along a asthenospheric viscosity of around 3 to 4 times 10 to the 18, which is the steady state value. However, none of our 1D Earth models fit all the GPS sites in all directions, and initial 3D models that we've tested also don't improve the fit. The Burgers rheology is the preferred rheology, but there's a question around the transient deformation not being detected in the GPS. And this is important because post-seismic deformation is potentially affecting geodetic measurements from across the continent, and this signal needs to be taken into account before we can use GPS to constrain geophysical models such as glacial isostatic adjustment. Thank you.
Thanks, Mads. If you will you like to take some question? I mean, if somebody has got anything, they can put it in chat box. I have one question. If nobody has got a question, then I can ask this. Sure. It's on your chat box. If you can see it now. Okay, I
can't see it in the chat box. No, maybe I can see it. Is it in the Q&A or the chat?
Oh, it's in the chat box?
Okay, no, I can't see anything in the chat box. Strange. Oh, there we go. Finite fault model derived from seismometer and GPS, sometimes quite different. Yes, that's true, and that's in general we take the finite fault model and scale it or test a range of uncertainties around its various parameters so that so it maximizes the fit to the co-seismic displacement of the GPS. I think that's what Grace has done here. She didn't talk about that, but I'm pretty sure that's what's been done.
Thanks, Mats. Thanks a lot. Thank you. I think with this, we can go to now it's 9:20, right? Yeah, we're taking slightly longer time, but that's okay, as long as talks are interesting. So now we can go to Eric. This is on giant regain, a comprehensive analysis of genetic genesis recordings in Antarctica for genetic and genomic application. So Eric, please go ahead.
Thank you. Can you see my screen?
Yes.
Perfect. Good morning, everyone. So today I'm going to talk about the Giant Regain project. Giant Regain, the geodynamics in Antarctica are based on reprocessing GNSS data initiative. It was originally initiated already in 2016 by Theo Dresden and the University of Tasmania. It aims for comprehensive and consistent reprocessing of all GNSS data on bedrock that is available from 1995 till the end of 2021. And our main goal in the end is to determine a consistent set of coordinate time series. By now, it involves 4 GNSS processing centers. That is Theo Dresden, the University of Tasmania, of course, and Ohio State University and Newcastle University. And in the end, well, the process time series, as I've seen before, shall be used for subsequent investigations in geodesy and geodynamics, of course, GIA, tectonics, or elastic loading deformations due to recent ice mass changes or SNB variations. Looking on the observational data, we have a lot of contributions from various networks and institutions, most prominently, of course, the IGS sites, ANET, VLN, Dev, and many more. There are also some sites that don't belong to networks, just single sites. We also included sites from South Georgia Islands, and you can see mainly a clustering of sites around the research stations. So you have a lot of sites in the Victoria Land and the Antarctic Peninsula, and quite a sparse spatial coverage in the East Antarctic, mainly the coast, as Matt showed before. Overall, we have 291 sites. About 50% of those are permanent sites. The other 50% are campaign sites or episodic sites. When we look at the observational data, well, we see in the beginning of the data set in 1995, there are barely any GNSS sites, but we get a steady increase of sites and observations till about 2016, with a big step after the IPY and after 2009. We have a big increase of observations. You can also see till 2008, there are a lot of observations in episodic style, and that's changing afterwards, where we have way more permanent observations. Yes, we have an overall time base of all sites of 10.5 years, so that's quite long. That's great for investigating long-term deformation effects such as GIA. And we have a decline of observations after 2020, I guess because of COVID, and so the missing maintenance season and missing collecting data. A second big part next to the observational data of the project is the metadata. So to produce a consistent homogeneous set of time series, you need to have a consistent set of metadata. When I talk about metadata, I mean informations on used receiver, antenna, marker eccentricities, and so on. So the metadata collection we did from, in the best case, observational protocols, public data archives, publications, sometimes photos that were not always in 4K high resolution, Rhinex header, and of course personal communication. But since some science reaching back till observations till the mid-90s, it's quite hard to sometimes access these informations. So it ends in an iterative process of generating time series and do some sort of verification of the metadata information. Of course, these information are of increased importance for episodic sites. Coming to the data processing. So right now we collected all the observational data. That's about 500,000 daily Rhinex files. These are distributed among these previously named processing centers. Those generate coordinate time series in a terrestrial frame, and these are afterwards analyzed and compared. Regarding the processing setups, we agreed on some quite fundamental setup. So we just use GPS only. We do not correct for non-tidal loading corrections because those might be of interest for subsequent investigations. And we, of course, use a uniform set of metadata. The major differences in the processings stem from different use processing softwares. So we have all the 3 big geodetic GNSS softwares included, like Bernice, Gypsy, and Gamut. A big difference might come from the reference frame realization and, of course, from the quality control setup. So like residual and RMS screening within the processing. Minor differences might come from orbit integration processes and the different parameterization of tropospheric corrections and things like ocean tidal loading corrections. Looking at the project progress right now. So as already mentioned, we distributed the observational data and the metadata. We are right now in the processing of these data on the different processing centers. So by now I cannot show you a complete analysis and comparison of all these time series, but I can show you some preliminary results. And with that, I show you some time series here for the site BENN of the ANET network. We see 2 time series, one from the University of Tasmania in a PPP setup. The other one is TU Dresden in a network solution with a regional reference frame realization. You can already identify some features that are quite, reconfirming for someone who's processing GNSS data. You can see these kind of features that are present in both processings. So it's probably on the data and not on the processing side to have these kind of features. An additional thing you can see already in the vertical component, you see these kind of dip in the time series here for UTAS. You cannot see that in the TU Dresden time series. That might be due to common mode error that is decently mitigated within a regional reference frame adaptation. A second time series I want to show you, and that is quite fitting after the last presentation, is a quite interesting time series and shows the possible applications of the published time series afterwards. It's the time series for DLL5, Carlini-Dahlmann, so at the tip of the Antarctic Peninsula. And it shows a somewhat picture book post-seismic deformation after a series of earthquakes in 2020. And looking forward for further investigations on this site. As an outlook, so the next steps after all processing centers have provided time series, we're going into the time series comparison, of course. So we're going to look into the power spectral density analysis, so differences in noise characteristics that might be explained by different reference frame realizations and adaptations. We look into the temporal behavior of Helmut transformation parameters with regard to a reference solution, e.g. IGS. We are going to analyze, of course, a frequency domain, looking into, for example, the amplitude of trachonitic harmonics. And as a result, we try to improve our understanding of the scatter of the resulting time series and infer some so-called processing noise resulting from the different software packages, processing strategies, and parameter choices. And as a final outlook, our first product we plan is a set of 4 separate sets of time series from the 4 processing centers. We do not plan to compute a combination product. They're going to be distributed as SINEX files for the geodetic users, and just plain time series of topocentric coordinate changes with intersite variance covariance informations for the non-geodetic users. And we're also going to include a step file for easy identification of steps and discontinuities. And we plan to publish the time series by the end of this year. And with that, I thank you for your attention.
Thanks, Eric. Thanks a lot. Thanks a lot. This is going to be a very useful product once it comes out. I have a small question. If do we have? You can put your question on the chat box. I have a small question. I see a strange transient in 2019. If you look at the time series, so what could be the reason for that strange variation, which was kind of recoverable? I mean, any guess of it?
Give me 1 second. You mean the this time series?
Yeah, you can see it here as well, but in the previous one it was quite. If you can go 1 slide back.
Once more. Okay.
Yes. So you see this in 2016, right? 2016, you can see a huge transient in north and east component.
In 2016, yeah, I mean, that is probably some tracking error. Just some, I don't would interpret it as a geophysical signal. That is pretty much an error, I think. And since it's evident in both processings, well, it's probably on the data. Just some tracking issues, I assume.
Okay. Yeah, it did not repeat any time, I mean, in any year.
No, we don't see that. And we don't see that at any surrounding sites either.
Thanks. So, in case there are no questions, thanks, Eric. Thanks again. So now we move to the next presentation by Dr. Hector Morapez, which is on GPS geodetic measurements to understand the deformation of the Earth's crust in Antarctica. Hector, please.
Thank you very much. Are you watching? Are you looking at the screen?
Yes.
Okay.
But not your presentation, I guess. I see some.
Okay.
Oh yeah. Yes.
Okay. Hi everyone. Good morning in India. Greetings from Colombia, South America. I am Hector Morapez, and together with the co-authors that appear on the screen, we will make a presentation about the activities that we have recently carried out regarding GNSS data processing in Antarctica. We work for the Geological Survey of Colombia, and we are members of the Space Geodesy Research Group of the Geohazard Directorate, responsible for the deformation studies in our country using GNSS technology. This is the first time that we venture into this data processing in Antarctica. We want to gain experience in geodetic research that will help us in the right interpretation of results. I think the title of our presentation is a very bold title, observing previous talks. I apologize. This is the agenda, and the motivation is that we are processing GPS station, GNS station, basically any station located in the tropics. That's mainly in Colombia, Ecuador, Venezuela, and also Panama, and some stations around the Caribbean plate. So the conditions are completely different than the conditions are the Antarctic. Therefore, it's of vital importance for us to understand how the GNSS signals behave in extreme severe conditions and the results, as well as the motion of the tectonic plates that interact in the Antarctic region and their deformation. Likewise, understand about the concept of GIA phenomena that is not present in the regions near of the Ecuador. Trying to understand the tectonic frame related to the Antarctic plate, we have begun to understand its great complexity. We have tried to present the main existing tectonic features in the study area in this map. And for this, we have used several sources. So light and the topographic base from natural RNA Topo 1. The boundaries of the tectonic plates and the movement have been obtained from the United States Geological Survey. We don't know if there is an updated one. The rift boundary system corresponds to the publication of Le Masurier 2013, and the location of volcanoes is extracted from Van Wyck et al. 2018. The maps have been produced using the ArcGIS software developed by ERRI. We also try to collect the data from the seismicity in the Antarctic region. The data source is the USGS and corresponds to the earthquakes of magnitude greater than 4.5 for the period of time from 1980 to 2022. The color and size of the balls indicate the magnitude and the depth respectively. Raines files of 2028 stations were downloaded from the IES and UNAPCO servers. Of that number of the stations, data from 180 stations have been processed so far, which are represented on the map. Of the 182 stations, for the possible calculation of velocities, 29 stations were discarded because they do not meet the minimum observation time of 2.5 years adopted by GeoRep, our working group. We have, regarding the problems presented, among others, that daily coordinates are generated, but in some cases, it is not possible to generate the velocities, or on the contrary, anomalous values are obtained out of any possibility. Also, in some cases, incomplete data has also been found for processing or lack of log files. We highlighted the Rio B4 station with more than 16 years of data, observation data. For data quality, we use the TEQ software developed by UNAPCO. As an example, we use the UPT station to compare expected observation versus obtained observation for the year 2021. Although there are 3 different sampling rates, it's established that the percentage of observations suitable for processing is greater than 88%. Similarly, the standard established by IES regarding multipath have been taken into account. In this sense, for the same VDUP station, the multipath values of MP1 and MP2 were analyzed and determined, obtaining values less than 0.5 and 0.75 respectively, which are those established by the IGS, as well as the value less than 10 for the signal to noise ratio. For GPS processing, we use the GPX software developed by GPL, Caltech, NASA, with the models indicated on the slide. The processing strategy is PPP. Of the initial 153 stations, 140 stations were finally selected after careful analysis for the generation of geodetic time series and estimation of geodetic velocities. The results are expressed in ITRF 2014, according to Altamimi et al. 2016. For the generation of the GPS time series, we have used the Hector software version 1.9, developed by SIGA, Space and Earth Geodetic Analysis Laboratory, center formed by the cooperation of the University of the Interior of Beira and the Geophysical Institute Infante de Luis. The minimum suggested observation time for the generation of reliable geodetic time series, and thus to obtain appropriate velocity solutions for purposes of tectonic interpretation, is 2.5 years of observation following the indication from Blewitt and Lavallée 2002. For the analysis of time series, the concept of offsets have been included. Until now, the offsets indicated in the time series of this presentation are instrumental corresponding to a chain of receiver or firmware update. So far, we have not introduced any offset related, for example, to earthquakes. For the generate of the geodetic time series of the continuous GNSS station, we apply the combined noise power law and white noise, and also to evaluate the quality of the applied noise model. Techniques such as the power spectral density diagram were applied. So these are examples in different time series that we have estimated in order to look in this case how the vertical component is behaving. One, this is very stable. This only the vertical descent, and the other the uplift. But we need to know what is going on in each stations. So these are the velocities that we have obtained so far, expressed in ITRF 2014. We were looking at previous work done by Gabriel et al. 2016-17 that expressed the data in ITRF 2008, and Sanuta et al. That is 2018 that expressed the data in ITRF 2014. And basically we can say that we found some agreement in these results, but however, we need to continue processing the data. One of the things that we want to do is to analyze the vertical components, thinking in the possibility and to understand what the GIA phenomena that is occurring in the Antarctic. At this station, the SLTR, we found the larger vertical component, and this is the time series is about 55 millimeters per year. It's a huge value that we are not accustomed to observe it in our country. So for that, it's very important for us to be working in this part of the world. One of the things that we we want to work to understand, but this is very preliminary, is the basis of the least square collocation. We have tried to start calculating strain radius using the GeoStrain software implemented by Goudarsi as a graphical user interface in MATLAB. We have not finished this task and probably will need to include more data, but frankly, we need to learn much more about this situation in order to what is going on in this part of the world. So our work is still preliminary. We will continue with data processing, including missing stations. Previous talk, I observed that there are possibilities to get some products. That means that maybe we don't need to process more data, or there is another servers that is possible to get some station available to be included in our processing. Is required to characterize the interaction with the place surrounding the Antarctic plate that we want to understand, to do, and also to generate appropriate deformation models, which are still in preliminary state for us. So we want to go step by step and to understand what the situation is there. Also, detailed analysis of the station location sites is required to analyze the vertical component and establish a possible relation with GIS models. So to figure out for us which stations are located in bedrock is very important. So that's one thing that we need to start looking on to understand and to interpret in the right way our results. Thanks. That's all. Thank you very much for your attention.
Thanks a lot. Thanks a lot, Hector. If you have any question, please, audience, please put it on chat box. Okay, Hector, in case, I mean, that's a good effort, in processing the data from all these stations, and I can only sort of provide some help that in case you need station data from our station, which is MAT3, you can ask for it, and we will be happy to provide it.
Thank you very much. That is one thing that we need to create some routines, and the other thing is I want to promote the students in Colombia to start looking at that part of the world, because definitely the Antarctic is the future area that we need to know very well. So
thank you very much. Thanks.
Okay, thank you, Vineet. Thank you very much for your offer.
So in case there are no more questions, we can go to the next talk, which is by Dvijendra Pandey, and I'm one of the co-author in this presentation. So it's on cause of large seasonal variation in deformation in Antarctica. Dvijendra, please.
Yes, sir. Is it visible, sir?
Yes.
Okay. So good morning. I'm here to present the
It's
cause.
not full screen yet.
Okay. Okay. Wait, sir. It's not come full screen yet, sir.
Not yet, unfortunately.
Oh.
If it doesn't work, you can still go ahead. But what I suggest is that if you can unshare it and then
Okay.
make it first
Full.
before sharing, make it full screen and then share it. Then
Okay.
it can work.
Okay.
Otherwise, you can just go ahead.
Okay, sir. Now it is come, sir.
Not yet, but you can go ahead, no issue.
Okay. So good morning to all. This is Dujendra from CSIR NGRI. I am here to present the cause of large seasonal variation in deformation in Antarctica. So first of all, we have to go about the outlook of the Antarctic plate and its motion. There is a large spatial variation in geological properties in Antarctica, and it's surrounded by the divergent plate bound margins. So it is a relatively a stable plate, and the plate motion varies from the 4 to 20 meter per year. And it's as we all know, the Antarctica is the.
You are still on first slide. We are still seeing your first slide. Is that correct?
No, sir. No, sir. I think some network. Is it come second slide, sir?
Yes.
Okay. Okay. So large, as I already told, that the Antarctica plays a important role in the functioning of global climate, as we are all concerned about the global warming and the climate issues due to the glacial melting and all, and the interesting area for the glacial feedback on the crustal deformation. So what are the factors affecting the crustal deformation? The tectonic movement, the volcanic eruptions, and the glacial movement, the glacial isostatic adjustments. What in this study, what I have seen in some of the stations, we have seen a large seasonal variation starting from the low latitude to the polar areas. Few of the sites I have studied is shown here. First one is CRDI. As we can see from the horizontal component, it's showing a large seasonal variation, as well as HOW, which is a polar region site. It also shows a large seasonal variation. And we have a Maitrey station of Indian base, and we can see here not as much the seasonal variation as the other two sites. So we are trying to, from the GPS time series, we can say that beside the circular motion, there is a large seasonal variation. It increases from the low latitude to pole. Here we can say in this from figure, this figure shows the detrended time series, horizontal time series at the different location. That is HOW is CRDI and the Maitrey. In order to know what are the possible regions for that large seasonal variation, we try to analyze the different factors which can affect the seasonal variations, like meteorological. In meteorological, we have temperature, pressure, humidity, ionospheric DEC content, hydrological loading, and others, glacial and tectonic movement. So from at the Maitrey site, this is the seasonal variation along with the loading and the meteorological parameters, temperature, pressure, and humidity. As we can see, there is the direct correlation with temperature with the horizontal time series variations, and also the loading is the consistent with the GPS time series. And other site is the CRDI site, which also shows the direct correlation with the meteorological parameter, temperature, and the hydrological loading. And for the more information, we have also analyzed the total electron content to know how it is correlated with the displacement time series from 2008 to 18. And we can also refer that ionosphere, it is the layer in atmosphere from 60 to 1000 kilometers, as Lee and Hong 2005 suggested. Distribution is influenced by geomagnetic and solar local time derived from the difference in regional geomagnetic field and different solar radiations. So from this study, we can conclude that the meteorological parameters, mainly the temperature variation, shows a good correlation with seasonal variation. A good correlation with temperature variation implies that hydrological loading and unloading of ice sheets in polar regions control the seasonal deformation. And what I have used here, the model ECM, ESM, GFZ derived displacement, mainly due to the hydrological loading, is consistent with the deep GPS time series. And from the TEC, we can see that it is not much consistent with the GPS derived seasonal variations. Thank you.
Thanks, Dijendra. I'll just wait for some questions, otherwise we'll move forward. Okay, I think there are no more questions on this. So, yeah, I think we can move forward. You can unshare your screen, Dijendra.
Okay, sir. Thank you very much.
Okay, then we have the next presentation by Belen Rosado Moscoso, which is on monitoring and surveillance of volcanic activity of Deception Island using GNSS techniques. I'm not sure whether we have the author here. Oh, we don't have the next two speakers. Do we have their recorded video presentation, tech team? No, okay. So in that case, okay, so the next talk also was by the same author on regional tectonic model of South Shetland Islands, Bransfield Sea and Antarctic Peninsula, and of course he's not there. So then in that case, we move to the next one, which is by Ashraf Kolali, elastic deformation due to surface mass balance variability in the southern Antarctic Peninsula. I'm not sure whether this author is there or not. I don't see him here. Are you there, Ashraf?
Hi, if you're there in the attendee, please raise your hand. We can put you back to panelist. And please make sure your names are written correctly.
Okay, so it seems he's not here. Oh, we can come back in case somebody shows up later on. So we move to the next one, which is by Lourdes Gonzalez Castillo. And that's on asthenospheric mantle electrical anisotropy and its role in glacial isostatic adjustment, insights from long period mantle rate measurements. I think he's there.
Yes, I am.
Oh, I'm sorry. I'm sorry. I'm so sorry. I mean, please excuse me for my bad.
No, doesn't matter. Doesn't matter. It's difficult to distinguish the names and so on. Well, I'm going to try to. Oh, okay. Oh, sorry. I'm going to try to share my screen. This. So, is it Is the full screen already?
Yes, 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 thanks.
Okay. Okay, then I'm going to try to move this over here. Right. Okay, now, well, good morning or whatever it is at your places. I'm Lourdes González. I'm a postdoc researcher from the University of Granada in Spain. And well, our study develops in the frame of the Goleta project from the Spanish Ministry of Science and Innovation. And well, Goleta is a multidisciplinary project that involves researchers from different institutions and countries. So it is a very international project, and we kindly invite all you to follow us on social media, especially on Twitter, which is the most updated one. Oh, I cannot. Great. Well, the Antarctica is affected by two processes that mainly condition the mantle structure beneath. Glacial isostatic adjustment processes imply mantle flows, whether from areas of ice accumulation to ice lost zones or towards surrounding oceanic regions. That is, that ice accumulation provokes lithosphere flexure and the subsequent divergent mantle flow. On the other hand, ice loss implies the lithosphere uplift and followed by the convergence flow, but in the same direction. In any case, mantle flows provoke an isotropy behavior of its physical properties, including electrical anisotropy. Well, the tectonic imprint of mantle anisotropy in the Antarctica is related to its geodynamic evolution. This continent includes two main domains separated by the Antarctic mountains, transantarctic mountains. The East Antarctica constitute an old craton with a thick lithosphere, while the West Antarctica is formed by the collision of different terrains and is much younger and tectonically active. Therefore, these two major domains have a clear different behavior. While the asthenospheric mantle structure in the eastern part should be mainly conditioned by the glacial isostatic adjustment processes, the structure in the western part is a result of geodynamic and GIA processes. Our research focuses on the Antarctic Peninsula and the Shetland Island. Tectonic in this area is the result of many geodynamic processes driven by the opening of the Drake Passage. So, accounting not only for the glacial isostatic adjustment, but also for the tectonic framework is essential to determine mantle structure and anisotropy. Well, magnetotelluric is a useful geophysical method that allows to delineate the electric conductivity structure within the Earth from shallow depths to asthenospheric mantle. The MT method is based on the simultaneous measurement of the natural variation of the Earth's electric and magnetic field in orthogonal direction at the surface throughout a wide range of frequencies. The lower the frequency is, the deeper depth of investigation. The MT variable most commonly used are the frequency-dependent transfer function between the time variation of the magnetic and the electric field. We will analyze the phase tensor and tipper vector parameters. While the phase tensors are sensible to resistivity contrast on depth, tippers show lateral boundaries. We follow the Bise convention, that means that the real arrows point in the direction of the laterally increasing resistivity. As proof of the usefulness of the method, MT allowed for determining the northwest southeast asthenosphere anisotropy beneath Tierra del Fuego in Argentina. This anisotropy is related to the spreading of the West Scotia ridge, active from 30 million years until 6 million years ago. During the first Antarctic season, we collected long-period magnetotelluric data at 7 stations located on both Antarctic Peninsula and Shetland Islands. LMT stations include three electrodes, north, south, and east-west oriented in an L configuration and 50 meters apart at least, recording the electric field. A flux gauge magnetometer measured the 3 components of the magnetic field. A GPS antenna are connected to the LEMI 417 and 420 data loggers. All stations recorded at least 15 days and 2 to 3 at the same time, allowing for a multivariate processing. Additionally, as a secondary objective, 22 stations measure broadband data at Deception Island to determine the deep structure of this active volcano. The seawater is the main conductor in the Earth's surface. So MT responses in nearby ocean areas are conditioned not only by the onshore depth structure, but also by the bathymetry. Therefore, the first step in any trustable MT study is determining the influence of the bathymetry. To do that, we have calculated a 3D forward model for an homogeneous half space and an accurate bathymetry. Topography is also included, despite its influence is at such a large depth is insignificant. To better understand what follows, I ask all of you to pay attention to the red arrows corresponding to the real part of tipper vectors. Model responses highlight that at shallow depth, which means high frequency, coast shape determines the MT responses. Tipper are orthogonal to the coast everywhere. I know that it is very difficult to distinguish in such a wide map, but trust me, it's easier if we zoom in each side. At mid-depth, the Bransfield Strait constrained phase tensor as well as tipper orientation unless the Brown Bluff station that is conditioned by the Antarctic sound effect. However, the Drake passage controls which is here or here, controls the MT responses at large depths. At Brown Bluff station, Weddell Sea adds to Drake passage and to Antarctic sound influence. So once we have already determined the bathymetry effect on our study area, data processing is proving to be a challenge and requires the adaptation of the FFT software from Frankfurt University to the features of the measurement equipment and the study area. At this step, we are focusing on tipper vectors from Copaitic and Brown Bluff stations, as they show the higher differences between the bathymetry and the data at all frequency range. At the high frequencies, tectonic influence the orientation of tipper vectors over the bathymetry. I mean, it is clear that it is a difference, a large difference between the bathymetry, the forward model response of the bathymetry, and the data, the field data. However, for longer periods, that is, large depth reaching the asthenosphere, deeper differences could be explained by means of electric anisotropy due to mantle flow. Once we get the final processing results, calculation of 3D forward and inversion models, including anisotropy, will help to elucidate the source of the mantle flow, whether it is related to the tectonic and or the glacial isostatic adjustment processes. Finally, well, for the next Antarctic season, we will measure at many stations, mainly located along the Antarctic Peninsula, as it is part of the Antarctic continent, and it is supposed to be more sensible to glacial isostatic adjustment processes. The integration of the upcoming data with the already recorded ones will allow us to calculate 3D anisotropic models constraining the electric structure of the asthenosphere beneath the Antarctica and determining the influence of the tectonic and GIA processes on mantle structure. And well, that's all. Thank you very much.
Oh, that's really a nice presentation. I mean, I never thought that there would be empty element in GIA analysis. So that's so nice. Very nice of you. In case we'll just wait for a minute in case there are any questions, then
wait, I'm trying to come back. Okay, here.
Vineet, can I ask a question?
Please go ahead.
Yeah, Lords, thank you for that presentation. It's a really exciting project. And I was really excited to see the plans for the further observations along the Antarctic Peninsula. You may know that we found with the GPS very strong uplift and evidence of low mantle viscosity under that region of the Antarctic Peninsula. And some unpublished modeling work we did suggested that you can only really explain that if the upper mantle is hydrated, which is perhaps not surprising given the former subduction zone. So it'd be really great to see whether you find quite a lot of water in the upper mantle from your measurements.
Okay. So I don't. I've lost you.
Yes, Matt, can you repeat your last sentence? I mean, so what he's asking is, did you find a lot of water in the upper mantle?
Well, I guess it was a comment as much as anything,
That's right.
because it was about the future measurements. Yeah, and
sorry, I cannot hear you. That's the I don't know why, but.
Oh, okay.
Oh, sorry. No, but it's. Oh. It's something related to my computer, but I don't know. Well, can you?
I can send you an email.
Something? Can you say something just to try to?
Can you hear me now? No.
What?
Okay. Vineet, can you hear me?
No, I think no. Yes.
Oh, you
yes.
can hear me now. Okay.
Yes.
So I was just saying that, yeah, we found high rates of uplift along the Antarctic Peninsula that seem to indicate very low mantle viscosities, like 10 to the 18, and some unpublished modeling work suggested that the upper mantle had to be hydrated for that to get that low viscosity. So I'm hopeful that you'll be able to constrain the level of hydration via your observations and models to come up in the future.
I hope so also. But, yeah. You know, we are in the first step and with data analysis and processing, and it is very a bit difficult, but on the other hand, very exciting, and we already have calculated some model also, but well, nothing definitive yet. This is why I cannot show today anything else, but it will come on the future. But anyway, I mean, we can keep in touch, and right, I think you have my email, Matt, and okay.
Thanks. Thanks a lot. Thanks a lot. I'm sorry again for addressing you with your wrong gender. I'm sorry again. We'll go to the next speaker. I saw him here, Jiniao. I saw him in the list of panelists, but I don't see him now. Is he there in attendees? Oh, he's there in attendees. Can you, tech team, can you promote him to panelists?
So he has to accept, we have already tried. He is in panelists now.
Great. Yeah, I can see him now. Yes. So the next presentation is by Jiniao Gao. That's on relationship among magmatism, lifting, and mantle melting of the Terror Rift, West Ross Sea. Jiniao, please.
शुभम, ये देखो चाइना वाले को।
Yes, we can see your screen. Please go ahead.
So we're not able to hear you.
We're not able to hear anything from your side. Jiniao, if you can. I see you are unmuted, but I don't see any flickering on your mic. So
So can you click on the mute button and select the audio input? So you have to select the audio input device, either your laptop or the screen or a camera, where the audio is coming in. So I'm going to mute you. Please try to unmute. Please unmute, sir.
Dr. Jiniao, can you unmute yourself so that we know that? Dr. Jiniao, can you unmute yourself? I see you are muted. tech team, can you try from your end so that
I have sent him a message also, sir. Can I, with your permission, I would like to move him to attendee and then bring him back, if that might solve the problem.
right? So, but let's first make sure whether the next speaker is here or not, because I don't see in the list of panelists. Adriana Ariza Pardo. I'm not sure whether we exchanged some emails, and it seems that she wanted to come in, but I don't see her here in the panelists or in the attendees. I don't see her here.
No, so she has not joined yet.
So in that case, this is going to be the last. He's going to be the last speaker. So we'll wait for him if he can.
I'll put him. I'll put him to attendee and then try to bring him back as a panelist.
Sure. Oh, I can see some flickering on his mic now. I can see Jiniao again, but if you speak something, hello Jiniao, how are you? Oh, we can't hear you. I see you are speaking, but we can't hear you.
Can you hear us, sir? If you could raise your hand, we would know you can hear us. Can you hear us?
He can hear us. It looks like he can hear us. Can you raise your hand if you can hear us? I think we'll wait for him because, he was here since the beginning of the session, so it will be unfortunate if he cannot make presentation just because of this technical glitch. So let's just wait for him. Please bear with us.
Why?
Oh yeah, great. Oh, great. Yes. So nice. We can hear you now. Please go ahead.
Sorry. Yeah, now I can.
You can go ahead, please.
Okay, thank you. My topic is about the terror lift. Yeah, it's located in the Victoria Land Basin in the western.
Share your screen. Please share the presentation. Share the presentation.
Not share?
Not yet.
Not yet. Okay. Not share? Why not share? Okay.
Coming up. Yes, it's coming up now.
Okay. It's okay.
Great.
Okay.
We can see, you can start.
Okay. So the terror lift in the Victoria Land Basin in the Western North Sea, and it consists of the Discovery Graben and the Lee Arch here. There are some seamounts along the terror lift, as well as volcanic activities in Falkland Island and Beaufort Island. They are Pliocene and Pleistocene volcanism, post-dating the Miocene phase of the terror lift major extension. We can deline two belts of volcanism. One is from the Erebus volcanic to the Melbourne volcanic provinces. Another is here to the Harwich volcanic provinces. Meanwhile, there exists a low seismic velocity zone beneath the terror lift, here, and here, and here. This is the effective elastic thickness of this sphere. It also is very small and affected by the temperature of the low velocity zone, especially in the two ends of the terror lift, the volcanic provinces. The chronological structure framework provides evidence for coeval emplacement of dikes on the two main north, west, southeast, and south-north striking trends, whereas tectonic and subvolcanic activity occurred in the adjacent cluster sectors at different times, and the mafic dikes display major trace element distribution typical of basalts from the oceanic islands. And the oldest volcanic rocks exposed in Erebus with age about 18 million years. And rift-related mechanisms began in North Victoria end dated between 14 and 28 million years. The mechanism of the polar sleeve anomaly between the northern basin and Victoria Land Basin activated during the 14.8 to 34 million years. So Rheology proposed a non-plantiform model in which the Southern Ocean fracture zones extend across northern Victoria Land as translithospheric strike slip systems, promoting local decomposition melting of widespread low melting point forms in shallow, weak, enriched layer. This intraplatonic displacements induced by plate circuit in the southern hemisphere appears sufficient to explain both the emplacement of magmas tightly linked to the active lithospheric structures and the episodic melting of a widespread enriched wind low melting point mantle source. In major continental rift systems, sailing over the rift system is commonly associated terms of end members models, active versus passive rift. And a genetic connection is commonly acknowledged between the lithospheric extension, magmatism, and the mantle plume activity. Although the mantle plume activity was not appropriate, the local decompression melting of widespread enriched wind low melting point mantle source is not clear. Yeah. And it is also difficult to illustrate volcanism post-dating after rifting along the tail rift. It is very young. For this reason, both have made a modeling for the West Antarctic rift system from distributed to coast extensions or narrow rifting of the tail rift by use of the finite element method. The key boundary and initial conditions are initial thickness of this sphere and crust is large, about 150 kilometers thick and 40 kilometers in West Antarctica. May be consistent with its acclimation history. The upper mantle, the temperature about 730 degrees Celsius, and also sufficient heat in crust account for 50% of the upper mantle temperature. Then, and the model demonstrated that the distributed extension throughout West Arctic between 105 and about 65 million years. Cooling of the upper mantle and the stressing of the extended West Arctic rift system lithosphere by 65 million years to restrict extension into the Victoria Land Basin. By 25 million years, the onset of rift related to magmatism in the tail rift. But there are 2 points to remain needed to consider. 2 stages of extension cannot fully reflect the multi-phase extension of East Basin Central Trough and the Victoria Land Basin, also under the tail rift. And why volcanism along the tail rift act after its rifting? So the dynamic mechanism for the tail rift needed to refine and address the relation among magmatism, rifting of the tail rift, and modeling the low velocity zone of mantle. So we try to answer some questions. to describe a multi-phase extension consistent with the geological and geophysical influence. Instead of constant extension, symbols switch from wide extension to focused lifting. Also, potential to the coupling between the lithosphere and the mantle, not one-way point from mantle or lithosphere. Further, the probe into the key links among the volcanism, magmatism, mantle melting, and lifting. We know that within the framework of plate circuit for the southern hemisphere, every tectonic blocks have experienced large spin drift, such as Antarctica relative to the Australia, and the West Antarctica relative to the East Antarctica. And especially the West Antarctic rift system should have passed the different location of mantle. Also, its structure changed with time, but the fixed position of mantle also changed with time. This change may be affected not only by the evolution of mantle itself, but also by different terrain blocks that have drifted over it. In this way, the fixed position of change mantle will react again the terrain blocks that have drifted over it. So according to the different published model of global plate model, combined with the rotation parameters of nine time nodes and the tectonic outlines of Antarctic plate, constrained by the geophysical data, we find the relative moments between the East Antarctica and the West and the East Antarctica since the 100 million years on the G-plate platform. So it's the over finite rotation. Yeah, it's the longitude and latitude, and it's the revolution angle. So the displacements predicted by the plate motion model are generally in line with the modern GPS observation. Yeah, the green is our results, and the red is the GPS metadata. They is generally the same. But there are difference in the movement speed between the East and the West Antarctica. The Antarctica plate moved towards the South America plate as a whole, away from the Australia, and it also keeps rotating clockwise. The absolute movement speed of the West Antarctica is large, and the East Antarctica is small. So let's look at the multi-phase extension of West Antarctica rift system. And its position changes relative to the today low velocity zone. This. From 105 million years to 85 million years, the eastern basin developed. Yeah. Here, from here to here. Then from 55 to 53 million years, the central trough developed. From the 43 to 26 million years, the Victorian basin developed. And from the 26 to 11 million years, the terrarift developed. We can see that the rift axis here over the eastern North Sea basin, overlapped the low velocity zone position. Just when the eastern subbasin had taken shape, maybe imply that the first phase of the West Antarctic rift system extension may account for the mantle or asthenosphere uplifting at its rift axis. Then in the process of Central Trough and the Victoria Land Basin extension along the both along the front of the Trans-Antarctica mountain, the low velocity zone position is located below here, below the central height, and in the common high respectively. So the high temperature of the low velocity zone may be shielded by these two high lines and not to be released. So volcanic activities may naturally absent on the seafloor before the terrarift rifting. At the same time, just before the terrarift had finished rifting, the low velocity zone position of mantle was still on its side. Then, as the West Arctic rift system continued to drift eastward, the terrarift and the front of Trans-Antarctica mountain located over the low velocity zone. So it can explain why the seafloor volcanism along the terrarift, the Erebus and the Melbourne volcanism came up later, after the terrarift rifting. The low velocity zone position of mantle may represent a failed subbreak branch of the triple traction until the first phase of extension of the West Antarctic rift system. Then it was resolved by these uplifts after the first phase of extension. It may also be related to the dome of the Maribyrnong land driven by the arm. So according to the TX 2019 Slaver key factor window form, we can simulate the temporal and spatial variation of the mantle seismic velocity. The blue represents the abnormal high velocity area. This may be the subducted ocean plate before the Cretaceous. The brown represents the mantle upwelling through the windows of the plate, where the mantle low velocity zone or maybe sub branch of the triple traction may exist. For the volcanism post-dating rifting along the terrarift and its two ends, we can attribute to the different types of faults. Besides of the low velocity zonal mantle, detaching faults, even the normal faults cannot provide enough depression space. Compared with the detaching faults and the normal faults, the strike slip faults can provide depression channels and make water can easily enter into the mantle. So water enters into mantle, which is apt to subtime and magnetize them. So depths to the Curia may larger than the depths of the morpho. This is the Curie depth, and it's the Curie depth relative to the morpho. Here, the Curie depth is larger than the morpho depth. So the transition from the strike slip faulting to the important water into the upper mantle. So after its initial organal extension, the terrific turns into oblique tension at its last phase of deform. And it's not the lift. Volcanism along the two neo-igneous alignments were activated mainly by strike slip faulting for northern the strike slip faults. So we can make some primary inferences. The plate motion model of West Antarctica with reference to the East Antarctica can simulate the movement and the extension of the West Antarctic rift system relative to the mantle. The low velocity zonal mantle beneath the rift would begin to take the shape of a sub-branch of the triple junction from the first phase of the West Antarctic river system wide extension. And its energy was also shielded by the uplifts. As the West Antarctic river continued to drift eastward, the terror lift had provided a channel for energy releases of the low velocity zone of mantle, which accompanied with the volcanism triggered by strike slip faults. So the strike slip faults take an important play on such a mechanism of modified mantle source, promoting mantle melting and magnetism, especially at the two ends of the lift. So it's my topic end. Thank you.
Thank you very much, Engineer Gahalaut. Yes, the role of VARs in the relative motion between Western and Eastern Antarctica is quite strange. I mean, despite being so much difference between the lithospheric thickness between East and West, despite so much difference between GI anomaly between East and West, we don't see much sort of motion, internal deformation across VARs using GPS observations. If I'm wrong, probably Matt will correct me, but that's what we see. But nevertheless, it's quite fascinating. Thanks a lot. In case we have any question, we can ask straight away, or you can put it on the chat box. Okay, it seems there are no more questions. So thanks again, Engineer Gao. Thanks a lot.
You.
Thank you very much.
It's my primary study.
Yeah. Thank you. And now we have come, we understand that other authors, probably they are not present in this session. So in case there's anybody who is there amongst attendees or panelists, can raise your hand, and they can make presentation in case they were absent during their scheduled time. And in case any of you has any question regarding any of these presentations, can ask, because we have some time available with us. Okay, in that case, we ended here. We had some 6 or 7 presentation, and it's really heartening to see that there was a lot of talk on GIA, which is very interesting. There was a presentation on post-seismic deformation, and then of course on strain rate. There was also a presentation on seasonal variation on GPS, as seen in GPS time series. There was also an interesting talk on MT work relating to GIA again, the flow of asthenosphere as seen through MT, and then relating it to GIA. And then the last talk was on magmatism, role of wars, and on terror rift. So with this, I think we end this session here, and I thank all the speakers once again. I'm sorry because of we couldn't adjust the time of each and every speaker, and I'm sure that there was a lot of inconvenience to some of the speakers. I'm sorry for that. And I think with that, we end it here. If there is anything from tech team, otherwise we end it here.
Thank you very much, sir.